You know, from that sour lemon in your iced tea to the soap you wash your hands with, acids and bases are literally all around us. But have you ever stopped to wonder what really makes one dangerous and another totally harmless? Well, in this explainer, we're going to pull back the curtain on the secret strength of these everyday chemicals. Let's jump right in.
And that brings us to the big question, right? I mean, lemon juice and battery acid, they're both acids. So why can you put one on your food while the other is something you should never, ever touch? The answer is so fascinating, and it all boils down to what we're calling their secret strength.
Okay, so first up, let's just take a quick tour of the acids and bases you bump into every single day and figure out what makes them tick. Just think about that sharp, puckering taste of a lemon or a splash of vinegar. That is the signature flavor of an acid. It's a taste our brains are hardwired to recognize. Now, on the flip side, if you've ever accidentally gotten a little soap in your mouth, yeah, you know that bitter taste? That's a base. Bases also have that distinctly slippery feel, which, as it turns out, is exactly what makes them so fantastic at breaking down grease and oil in all sorts of cleaners.
So, what's happening on the tiny molecular level? It's actually pretty simple. When you drop an acid into water, it gives away or donates a proton. You can just think of them as generous proton donors. That's their whole job.
And a base? Well, it does the exact opposite. It's a proton acceptor. When it's in water, it's actively looking to grab onto those free protons, which makes it the perfect chemical dance partner for an acid.
All right, so we obviously need a way to measure all this proton donating and accepting that's going on. And that's where the famous pH scale comes into play. Let's take a look at how it works.
The pH scale is a super handy ruler that runs from 0 to 14. Anything that lands below 7 is considered acidic. Anything above 7 is basic, which you might also hear called alkaline. And right there in the middle, at a perfect 7, is neutral. Think of pure water.
And now, we get to the heart of our question. What is the real difference between that dangerous battery acid and the lemon juice in your kitchen? It all comes down to this critical and often misunderstood distinction between strong and weak. This is the secret we're here to unlock. First things first, we have to bust a huge myth right now. In chemistry, the word strong does not mean concentrated, and it doesn't even necessarily mean more corrosive. Getting this one idea straight changes absolutely everything. The secret is a cool concept called dissociation. It's really just a fancy word for how a molecule splits apart into ions when you dissolve it in water. The key isn't that it splits, but how completely it splits. And why does that happen? Well, it's all about how tightly that molecule is holding on to its proton. Some have a really weak grip and let go super easily, while others hold on for dear life.
You know, here's a great way to picture it. Think of a strong acid or base like an all-in sports team. The second it hits the water, every single molecule jumps into the game. We're talking 100% dissociation. But a weak acid or base? That's more like a team full of bench warmers. Only a few molecules decide to play at any given time, while most of them just sit on the sidelines. That's partial dissociation.
So let's look at a real-world strong acid, like the hydrochloric acid that's in your stomach right now. If you were to put 100 molecules of it into water, all 100 of them would instantly split apart. Bam! You'd end up with 0 intact molecules and the absolute maximum number of proton-donating ions possible. That's what makes it so strong. Now, let's compare that to a weak acid, like the carbonic acid that makes your soda fizzy. If you put 100 of its molecules in water, maybe only one of them will actually split up and donate a proton. The other 99? They're just hanging out on the bench, totally intact. See the massive difference? It has the potential to be acidic, but it holds most of its power back. Okay, so this difference in dissociation, this all-in versus bench warmer thing, it has huge real-world consequences. It affects everything from whether a solution can conduct electricity to how your own body functions.
Let's just break it all down side by side. Because strong acids dissociate completely, they create way more ions, which pushes their pH values to the extremes, either really low or really high. And look at conductivity. All those free-floating ions make them great at conducting electricity. Their reactions are super fast. Weak acids and bases, though, they have more moderate pHs, they're poor conductors, and they react way more slowly.
And this is exactly why this distinction is so vital. Your body absolutely needs a strong acid in your stomach to just obliterate the food you eat. But the acetic acid in the vinegar you put on your salad,
That needs to be weak, otherwise it would be totally unsafe to eat. In contexts like these, strength is, well, everything.
So what if you're still not quite convinced that strength is more important than concentration? Let's prove it with a little head-to-head comparison. A dilute strong acid versus a concentrated weak acid.
First up, our dilute strong acid. Now we've only put a few drops of this stuff into a whole lot of water. But because every single one of its molecules goes all in and donates a proton, it can still achieve a very, very acidic pH of 2.0.
Now for our concentrated weak acid. Even though there are way more acid molecules packed into this solution, most of them are just sitting on the bench, remember? And the result? A pH of 2.2. Get that? The dilute but all-in strong acid is actually more acidic than the jam-packed concentrated benchwarmer acid. Wild, right?
Finally, let's wrap this up by looking at what happens when these chemical opposites actually meet. It's this really elegant and powerful process called neutralization. It's really just a simple four-step chemical dance. You've got an acid ready to donate its proton. It meets a base, which is ready to accept it. They react, the proton gets transferred, and what do you end up with? Two of the most stable and common substances on Earth, water and a type of salt. Here's the classic example. You take hydrochloric acid, a super strong acid, and you mix it with sodium hydroxide, which is a really strong base. And what do you get? You get sodium chloride, which is just regular old table salt, and pure water. The two dangerous reactants completely cancel each other out to form something totally harmless.
And that brings us to one final mind-bending thought. Your blood maintains a perfectly stable pH thanks to a delicate balance of weak acids and bases. They act as buffers, only donating or accepting protons when they're absolutely needed. So just think about it for a second. What would happen if those crucial acids in your blood were suddenly strong ones, going all in all the time? That right there is the power of understanding strength. Thanks for tuning in.